Welcome to a new test and teardown video. This time it's a memory voltmeter from Gay Milano. They call this the type MTA. And I just had to buy this one because of this memory voltmeter. I think that sounded just too good to let that one go. It is from 1974 and it's 3.9 kilos, super heavy. It's absolutely special, by the way. I was able to find the manual with all the technical details and specifications about how this one works and what it can do. Let's look a little bit at a few pictures from the manual. So this is the first page, and we see in the upper top right corner it says 1174. So it's from November 1974 and it's patented. That is interesting. On the next page we can see what it's supposed to do. So it's peak voltage measurements of single or repetitive pulses and down to 15 nanoseconds. So that means it can measure over a long time and accumulate the highest pulse for you, so you can monitor something that is probably unstable or whatever is going on. Here it says a little bit more about what it's supposed to be used for. Disturbance monitoring of interference for like power supplies or input voltages for whatever instrument you're working on. The manual also consists of some curves that explains the peak detection. For example, the 50 nanoseconds or the 10 microseconds and so on, the different time filters for the peaks. It also shows how the polarity selection works. And here it's even more crazy. I thought the switches, there was a release mechanism fault, but that is not the case. You can select positive, negative, or both at the same time, and then it will store and read and accumulate positive and negative peaks. And there's also the DC-AC filter, where you can accumulate the AC component or the DC component. It also shows how the high-pass filter works to figure out if you got a low frequency or a glitch on a pulse. I think that is also a very useful feature. Due to the isolation and all that in this instrument, this is a special isolated BNC connector. See this little extra Teflon ring in there? So I think I can just use a normal BNC connector like that, and see, now my ground is not connected to the chassis, so I can still measure voltage differential on this cable. I hope this is how it's supposed to work, because I don't have a connector that can connect to that as well. And it seems to be, see, there is a ground or shield, and then there's the low and the high. So I believe that I can use a normal BNC connector for this one. It just shows me that we can have a 1000-volt isolation between this chassis and whatever it is I'm measuring. I also find it a little bit confusing. What is going on here? They also says this in the manual, there is an extra chassis inside for shielding, but it's also talked about the battery option, and it is very heavy. So maybe there's a battery inside. And here is the label where we can see the full address and numbers and serial and all that. Let's try and open this thing and see what is inside. Okay, so that is interesting. So the idea is, I have no idea yet what this is doing, but the idea is for disassembly, I think I should be able to... Yes, I was. And of course the mains connector also fit through this hole. So that means I will be able to remove this case and then get into that one. Okay, there was supposed to be a connector here. So this is the inner chassis, and we find a nice little label. So maybe, oh, it says here 17 August 78 battery change, and some other dates and even some names. So there's something about a battery that was changed. Oh no, it's probably a leaked nasty battery in here. So yeah, I can hear that something is loose in there. So let's open and investigate. What have we got right here? So the blue is positive, yellow is negative. All right, and some, ooh, nasty. And here is a little battery pack. I better go and clean this up a little bit. How is this working with this memory? I can't wait to figure that out. And why didn't they why didn't they use red and black? That is some funny. A little room for the transformer. So this is a lead acid battery, I guess. What a cute little 6-volt lead acid battery. I mean, this is probably the smallest I have ever seen. It's the cutest. You see, we need some compressed air to make this nice and clean. So this is the bottom part where we can see the circuit board. And is that a counter? LS93 and LS93, right? So this is probably for some timing, and optocouplers for some triggering, but the rest is just analog. So I bet it's storing the voltage somehow into probably some of those capacitors or something like that, right? Power supply, rectifier, and all diodes. Pretty simple. Mains entry. It looks a little bit like, if we zoom in here, mains cable was supposed to be a 3-wire with proper protective earth on the center. See, this black cable here goes all the way to the front metal, and mains go via resistors and then capacitors to that protective earth, and then resistors and a capacitor, and this will be the transformer input via the switch. And the other part of the switch, that is the battery. So it's turning on both mains and battery at the same time, probably for charging. And if you don't have any mains input, it's just going to run on the battery. So battery is probably needed as a part of the regulation or power supply or something like that. I think we need to consult the schematic before I proceed powering up this unit. That was interesting. By looking at all the PDF files I found online, I found a very, very interesting block diagram that shows how this unit works. And that is so cool. Look at this. If we start to the right, the two counters, they're 4-bit each, and together they form an 8-bit counter. So the 8 bits, they are now connected via resistors, and creating a digital to analog converter. And then when it's counting up using this clock source, it reaches a point where this comparator compares the input with the counted value, and then it stops. And of course, you can auto reset or variable reset this, and then it starts again. So this is definitely a good way to store the analog readout. So there's a digital to analog converter, and this is of course to make an analog to digital storage. That is the main feature of this. So yeah, I totally love it. Let's look a little bit on the more detailed diagrams. We can see the input amplifier and the input attenuator or voltage range selection. They added a lot of capacitors over all the resistors, and this way making it fast. The rest is just a lot of transistor amplifiers, balanced differential couplings, so that's quite normal. On the next page, we find the oscillator, comparator, output amplifier, memory register. So they call this a staircase generator. It is, of course, the counters and the 8-bit converter. And the fun thing here is they did not use the R2R principle, but instead they're using 8 resistors. I think that is very interesting. Why would they do that? It is definitely not as linear and as accurate as making it the R2R way. And then they're using transistors as well. You need 8 transistors to handle it that way. Complicated. Here is the schematic for the power supply. And as we see it, definitely the battery is an important part of the power supply. But to the left of the battery, we see a 7.5 volt Zener diode. So that means I should definitely be able to disconnect and remove the battery and still power this up, because I will have a pre-regulated 7.5 volt going into the rest of my system. It is of course a little bit over voltage compared to the 6 volt battery, but of course the 6 volt battery fully tip-top charged will be the 7.5 volt. So I definitely expect the whole circuit should be able to handle 7.5 constantly. As we see it here, we can see we got 2 power supply voltages, a 5.2 and a 2.1. So that is of course what I need to double check and verify in case this system is not working. That is what I would start to play around with. On the power supply schematic, we can also see how the internal box and the external box is made and how they're connected together via capacitors and all that kind of stuff. I still don't understand exactly why they wanted to do this. There isn't really any reason to do this, because everything is connected together via capacitors. So that means noise and AC and all that kind of stuff just goes straight through. So it's just like an isolation for a DC for almost no reason. So with all this reading and preparing and all that, I feel we are ready to power this up. For the first time I got 230 volts input, and let's try and dial this one. And that is exactly what I was hoping for. A nice little lamp. And we don't have a 0. But if I push the reset. Aha, so this is manual reset. And then it counts up to this one. So I am in 10 volt range. And that was 7 volt input, and it hammered it all the way up. So that is and now it's zeros. Okay, interesting. Let's try the 30 volt range. And again, our 7 volts. Okay. So that is 7 volts in the 30 volt range. Aha! Now I think I got it. Now we have about 7 volts. And it is because this unit is supposed to be working together with an external divider for much higher voltages. So that is why this unit here accepts a much lower voltage. So if we go to 10 volt range, reset, this is, hello, the input is of course floating. Let me try and short the input. There's probably something with some of those. Switches. And there you have it. Okay, let's try and open it and try and give it. Now it works. Now we have the 7 volt. Okay, so I was wrong about the ranges or the external divider. There is something about an external probe or voltage divider that you can put in front of it to give you 10,000 volts, right? But then you will have to manually multiply. But anyway, it seems to be more or less working. But it's not super accurate, but that is how it is so far. Let's try and short the input again. Reset. And let's try and open it. Yeah, just touch it with my fingers. So the input impedance is very, very high. And here's our 7. Okay, so now it's 7 volts. Good. So there was a glitch of overvoltage. I really love it. So there should be a fast reset. Yeah, exactly. See? And then tick, 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 tick. So once a second here, it will reset. So here's my 7. Yeah. And then it resets. Wow. How about that? So here you can see what I'm doing with the input. Give it a little bit more time. I totally love it. This is really, really cool. What we should definitely try is to see if we can give it some really, really small pulses and see what is going on. And I will then clean all the switches. Let's try and play with the pulse mode. I'm inputting some pulses, you can see here on the scope. And at the moment, my pulse width is 200 microseconds wide. It is a 2 volt pulse. And let's see if we can, probably show this a little bit better. So it goes to 2 volt. And then this one is set for auto reset. What if I put this filter here, or this response time setup here for 100 microseconds, okay? And let's play with the pulse width. So if I change my pulse width to 100 microseconds, it is now a lot smaller here on the scope, right? We can now zoom in. So now we have 100 microseconds on the scope, and it's still reading 2 volts, probably a tiny, tiny little bit less. But now I will go in with the dial and make it less. 90, 50. Yeah. So now it's 50 microseconds, and we're starting to see a decrease. And let's go down to 20. Maybe 10. See, now my input is 10 microseconds, and it shows now half of the signal. But what if I change the setting here? To be ultra fast. So this is 20 nanoseconds or 10. So 10, it's filtering a little bit on the response, and then there is no overshoot or anything like that. In super fast mode, it reads a little bit too much. So it hammers over. That is interesting. What if I try the 1 microsecond? Then it also goes a little bit too far. So it's not as accurate. Maybe my signal got a little bit of overshoot because my cable here isn't correctly terminated. And my generator is insanely fast. My rise time is 2 nanoseconds into a cable that is not proper terminated. So that is why you see those overshoots. What if I make it as fast as I can here so we have most possible overshoot? And now let's try and change my rise time so it is 100 nanoseconds. I still see overshoot. Rise time is of course also a rise fall, also 100 nano. And I still see the, what if my rise time is 500 and my rise is also 500 nanoseconds and my pulse is 10. Maybe my pulse needs to be much smaller. Let's go into 1 micro. Yeah, it still overshoots. That is a little bit interesting, so I don't think it's supposed to be like that. Now my pulse width is only 1, and now it reads a little bit less. So I believe this all works, but this is just how accurate this thing is. Now my pulse is 2 microseconds wide, and now it's accurate again here. Let's try and zoom in here on my oscilloscope so you can see the input curve is nice and fine. Yeah, I'm sorry it can't really handle focus. See, oh, now this is in focus, and then, I mean, there is no such thing as everything in focus mode. More or less, maybe go further away. But I definitely love this instrument, and it seems to be working now. So let's just try a little bit faster. So now my input pulse is 100 nanosecond wide. It still happens every second. And it's still unterminated, the cable. And this is why it's looking like this. So my rise time and is quite nasty like that, right? And we can of course change the pulse width down to like 50 nanoseconds, and then it will start to read a little bit less. So it should have been much faster than 50, but it still detects it quite all right. And there you have, my pulse is not super nice. So my pulse is definitely less than 50. So that's probably why. We need to have the stable part of it. So now I set up my generator for 100, and then see, the stable portion of my signal is about a little bit more than 50, and that is why this meter now reads more or less the correct value. So there is just one little tiny detail to mention, and that is my final idea with this instrument. What I want to do, see, it was supposed to, originally it had another funky type of mains connector. Somebody of course removed that one, and then always pull the plug when you're poking around with mains connectors. Anyway, the hole here is much smaller, so I can't really put in a modern IEC connector directly, but look at that. It's not a lot. I need to cut this hole bigger. What I can do is remove all this, and then I will be able to put it in. And it must be located like this, with an offset. And then it will fit through this larger hole at the back. And then it is definitely fixed for modern use. I think there's definitely something cool I can use this instrument for. So that is clearly another keeper for my funny collection of cool instruments. So I hope you liked it, and you're so welcome to comment. Is there any kind of cool experiments or usage scenario you can come up with that I can use this for? Come with some suggestions of real life experiments. I would definitely love to hear what you would use this one for. I'm quite happy about how that turned out. So I put in the connector right there, and I offset it so it's going to stay inside the case like that, and then I can reach it from the outside from that other hole. So that concludes this unit. Yeah, I had to move it this way for this to work, so it's not the most beautiful hole I made in here, I must say, but nobody can see that one.